Okay, angular milling by angled workpiece. Positioning work to a layout line using a surface gauge for milling an angular surface. Using a protractor to position a workpiece in a vise for angular milling. The protractor head is referenced to the top of the solid jaw. And using an angle block to position a workpiece in a vise for angular milling. A sine bar can be used to very accurate positioning of a workpiece for milling angles. After the work is clamped to the angle plate, it is a good idea to remove the gauge blocks and the sine bar before machining to protect gauge blocks from chips during milling. Aligning a large workpiece with a protractor using the edge of the machine. Positioning a large workpiece using an angle block and square. The square provides a reference surface related to the table movement. Setting a swivel base vise and a protractor using an E-dovetail as a reference surface. Indicating an angle block reference angle or against the solid vise jaw. The work stop keeps the angle block from moving. Milling an angular surface with the work head held in a swivel base. Face milling an angular surface of a workpiece held in a sine vise directly clamped to the machine table. Note that the gauge blocks have been removed from the vise to keep them away from chips being produced during machining. To align the turret, run the indicator across the angle plate by moving the ram slide back and forth. Adjust the turret until the indicator reading stays constant. In this picture, the angle plate is aligned using pins of the T-slots of the machine table. A protractor can be held against the quill to check the angular setting of the mill head. Hold the protractor head against the solid vise jaw so that the blade is in line with the direction of the angular movement. Indicating an angle block held in the vise by moving the quill. When the indicator reads 0 across the block, the angular setting is correct. With the head tilted to the desired angle and the angular surface can be machined using A, face mill, or B, peripheral milling. Milling step, slots, and key seats combines face and peripheral milling. Basic step milling may be performed with standard end mills, shell end mills. Slot milling may be performed with standard end mills, key seat cutters, and plain key seat Woodruff key cutters. Touching off and roughing an end mill to set the reference for step depth. Touching off a roughing end mill to set reference for step width. And in A, the step is being rough machined with about 20th of the desired size with a roughing end mill. Notice the uneven surface finish of the wall at the bevel at the inside corner. The first cleanup pass with the finishing tool, about 10th thou, is being machined from both the vertical and horizontal surfaces. Notice that the finishing end mill smooths out the vertical wall and makes the sharp interior corner. And then C, a final climb milling pass is being machined to finish the step. Only about 3 thou is being cut or machined from both surfaces. Milling a slot wider than the tool's diameter. First mill along the center line in A, then step over equal amounts to reach the required width in B. There's milling a through slot. And then there a plain key and a key seat. A portion of the table showing a square key seat, dimensions, and tolerances. When using an edge finder to touch the side of the shaft, be sure the tip is below the center line of the shaft. Positioning the spindle in the center of the shaft using an edge finder. So 1, edge find the shaft. 2, raise the edge finder above the shaft. And 3, move half the edge finder tip diameter plus half of the shaft diameter. Instead of using an edge finder to locate the center of the shaft, position the tool near the outer edge of the shaft, then rotate the cutting tool by hand while moving the table 1 thou at a time until the paper is pulled by the cutting edge. After the paper is pulled by the tool, raise the tool, then move the paper thickness 1/2 the tool diameter and 1/2 of the shaft diameter. So you're just adding the paper thickness on this instead of an edge finder. Be sure to use a center cutting end mill when milling a key seat or closed key seat. Milling a closed plain key seat. Milling a T-slot and a dovetail slot. So of course key slot's A and dovetail is B. A Woodruff key and key seat. To position a Woodruff key seat cutter to the center of the shaft, first touch off the top of the shaft using a strip of paper. Then move the cutter away from the work and raise the knee of the thickness of the paper, 1/2 the cutter width, and 1/2 of the shaft diameter. To locate the Woodruff key cutter from the end of the shaft, first touch off the end of the shaft with a strip of paper, then move the paper thickness 1/2 of the cutter diameter and the desired distance. And A, machining a Woodruff key seat, and B, the finished key seat. Milling a slot with a stub arbor mounted slitting saw. Alright, milling radii. Mill external radii with corner rounding and concave milling cutters. Mill internal radii fillets with a ball end mill and radius end mills and convex cutters. Speed and corner rounding, concave and convex cutters often need to be reduced because of the large contact between the tool and the workpiece. Speeds for ball nose and bull nose end mills can be equal to those for standard end mills. Two methods for milling an external corner radius. So one on the left, position tool so the upper edge is about 10 thou above the tool's top surface of work. Mill passes by moving X or Y axis until tip lightly touches the wall. And then 3, raise knee to take light cuts until upper edge lightly touches top surface. And method 2, on the right, position tool so that the tip is about 10 thou from the work edge. Mill passes by raising the knee until the upper edge of the tool touches the top of the work, and then move X or Y axis until tool tip touches the edge of the work. A radius on the bottom edge of a workpiece machined by a stub arbor mounted radius cutter. And then a full external radius machined by a stub arbor mounted on a concave milling cutter. When roughing an internal corner before machining a fillet, 3 different methods can be used, as shown in A, B, and C. In all cases, be sure to leave enough material for radius of the tool. Then a bullnose end mill can be used to machine the fillet. So on the first one, leave material at least equal to the desired radius. Bullnose the end mill, and material removed by the bullnose end mill is on the right or left there. Alright, on 2, leave material equal to the radius on the bottom instead of the side, and then finish it out. And then the third option is just to leave the whole corner there. Unmachine square at least equal to the desired radius, and then bullnose the material out. Use a small step over amount when machining a fillet and a bullnose end mill to avoid noticeable steps in a horizontal surface on the right. Radius slots on A, and then a spherical depression machined with a ball end mill on the right. Pocket milling. A pocket is an internal part or feature machined into a surface of a workpiece. An open pocket breaks through at least one edge of the workpiece. A closed pocket is completely contained within the outer edges of the workpiece. It is common to rough a larger diameter end mill finish with a smaller one. A radius slot machined on the side of the workpiece with a convex milling cutter mounted on the stub arbor. Examples of A, open pockets, and B, closed pockets that can be machined on a vertical mill. Rough machining of a pocket is often performed with a larger diameter end mill than the finishing operation to remove material more quickly. Material left in the corners is then removed by a smaller radius of the finishing tool. a coordinate map for milling a rectangular pocket, a typical pattern for milling a square or rectangular pocket from inside to outside. From the starting point, incrementally step over about half to 3/4 of the end mill diameter and feed the tool in a clockwise direction.